Welcome to this presentation. You are watching Vlsi Design Lecture Series, and today we are going to talk about timing and control. This presentation will give you a picture of memory model as a complex entity whose operation is governed by a well-defined sequence of actions such as address latching, word line decoding, bit line pre-charging and equalization, sense amplifier enabling, and output driving. To be operational, it is essential that this sequence be adhered to under all operational circumstances and over a range of device and technology parameters. A careful timing of the different events is necessary if maximum performance is to be achieved. Although timing and control circuitry only occupies a minimal amount of area, it's designed as an integral and defining a part of the memory design process. It requires careful optimization and the execution and repetitive spice simulations over a range of operating conditions. Over time, a number of different memory timing approaches have emerged that can be largely classified as clocked and self-timed. Whereas this clocked is used for DRAM and self-timed is used for SRAM. Now let us see the DRAM approach, that is clocked approach. Since the early days, DRAM memories have opted for a multiplexed addressing scheme where the row address and column address are presented in sequence on the same address bus to save package pins. This approach has survived many memory generations and is still in use today, although it is getting increasingly awkward and in disparity with the system level requirements. In the multiplexed addressing scheme, the user must provide two main control signals, that is RAS, row address strobe, and CAS, column address strobe, that indicate the presence of the row and column addresses respectively. And another control signal W indicates if the intended operation is a read or write. These signals can be interpreted as external clock signals and are used to time the internal memory events. Similar to the synchronous clocking approach, the RAS and CAS signals must be sufficiently separated so that all the ensured operations have come to completion. Here you can see the simplified timing diagram of 1/4 mbit DRAM memory and some of the imposed timing constraints. The full specification involves more than 20 timing parameters, all of which have to be held within precise bounds to ensure proper operation. Obviously, generating the current timing signals for these memories is a non-trivial task. All the internal timing signals such as EQ, PC, SE signals are derivatives of the external control signals. To maximize performance, some of those signals have to fall within the very precise intervals. For instance, the SE signals cannot be applied too early after the word line decoding is started, since this increases the sensitivity to noise. On the other hand, postponing it to for long slows down the memory, and the separation of these events is a function of the word line delay that might vary with temperature and process variation. It is a common practice to adjust the timing control or timing interval with operating parameters by including a model of the word line, that is dummy word line, in the timing generation circuitry. And this delay module tracks the delay of the actual word line accurately, making the memory more robust while preserving the performance. It is thus fair to state that the DRAMs combine a synchronous approach at the global level with self-timed techniques for the generation of some of the local signals. Now let us have a look into the synchronous and DRAM memories. One of the main challenges of the DRAM memory is the large access time and the low data throughput. With ever increasing speed of the microprocessor and their SRAM caches, the performance gap between the processor core and the main memory is getting larger. And this gap is becoming one of the main challenges in high performance system design. To address this problem, high-speed DRAM synchronous memories such as SDRAM, synchronous DRAM and RDRAM, rambus DRAM have been introduced. These memories present a major departure from the RAC-CAS timing model of traditional memories. While keeping the core of the memory relatively unchanged, Synchronous DRAMs exploit the fact that the core is highly parallel. In other words, for every given real and write cycle, a large number of bits can be read or written at the same time, at a relatively low speed. Bringing these bits in and out of the memory chip can be accomplished with a high-speed synchronous interface operating at a speed close to the processor clock frequency. And this comes at the penalty of extra latches and buffers at the interface into the memory core, as well as the high-speed circuitry to support the high data rate interface. The main contribution these memories offer is a redefinition of the interface into the memory. As long as data is written in large sequential blocks, this approach has proven to be very effective. Consider, for example, an RD RAM, that is, input-output data is transferred serially on a narrow bus taking several clock cycles. The bus is operated at a very high speed, however, and uses efficient packet protocols. Thus, a large amount of data can be transferred in a very short period. Multiple memory chips can be connected to the bus called the RAM bus channel, and you can see the schematic diagram of input-output circuitry of the RD-RAM memory. Next, what we are going to see is about SRAM, self-timed approach. In contrast to DRAM, SRAM memories have historically been designed from a globally static perspective. A memory operation is triggered by an event on the address bus or RW by signal. No extra timing or control are needed. Such an approach seems to be imply a fully static implementation for all circuitry, such as decoders and sense amplifiers. A change in one of the input signals and then simply ripples through subsequent layers of the supplementary. And such a fully static approach is not visible for larger memories for both area and power dissipation considerations. SRAM memories therefore use a clever approach called address transition detection to automatically generate the internal signals such as PC and SC upon detection of a change in the external environment. The ADD circuit plays an essential role in the architecture of SRAM and PRAM models. It acts as the source of the most timing signals and as an integral part of the critical timing path. And speed is thus an utmost importance. A possible implementation of ADD circuit can be shown, and it consists of a number of transition triggered one shot, one per input bit connected to a pseudo NMOS NOR configuration. A transition on any one of the input signal causes ADD to go low for a period TD. The resulting pulse acts as a main timing reference for the rest of the memory, which results in a huge fan out. Adequate buffering is thus recommended. And in a more elaborate view of SRAM timing can be found in the case of studies. And the memory reliability depends on both SRAM and DRAM are operating under low signal to noise conditions. And that is maximizing the signals while minimizing the noise contributions is essential to achieve stable memory operation. Another problem in memory design is the low yield due to structural and intermittent defects. Now, a tremendous effort is being made to produce the memory cells that generate as large a signal as possible per unit area. Notwithstanding this effort, the produced signal quality decreases gradually with increase in density. For instance, the DRAM cell capacitance is degraded from approximately 70 picofarad to 16 kilo memory to below 30 picofarad for the current generation. Simultaneously, the voltage level have decreased for both power consumption and reliability purposes. Voltages at or below 1 volt are then norm for newly designed memories. The main reason for being limited and voltage stress, and that can be endured by the very thin oxides used in cells. Consequently, the signal charge stored on the capacitor has dropped with a factor from 64 kilobit to the 64 MB generation. The fact that this drop is only that much despite the cell area reduction and that over the same period of time is solely due to various cell innovations. So at the same time, the increased integration density raises the noise level due to the coupling. And while the problem of word line to bit line coupling capacitance was already an issue in the early 1960s, and closer line spacing has brought the bit line to bit line coupling into the limelight. Thank you.